Welcome to our class, and today we continue with our lessons on how to, first of all, write a circuit in Noir, generate a proof, and then deploy to Sepolia, and then do the verification. So that is what we'll be doing today, from circuit compilation to on-chain verification using Noir and Foundry. So what is the motivation of our lesson today? One, we know what the zero knowledge proofs are, that they enable the proving of statements without revealing the underlying witness or data. So Noah, as we've always said, does simplify the building of ZK circuits, turning mathematical constraints into proofs. And that is what Noah does. So we'll be using Noah, therefore, to write ZK proofs in today's lesson, then generate a proof for that, and then deploy a contract to Sepolia, and then verify the proof on chain. So that is what we'll be doing in our today's lesson. So once a proof is generated, it can be verified. You can do the verification either locally off chain, or you can do the verification on chain using Solidity Verifier. That is our, okay, we will do both. We will do both in our today's lesson. We'll see how do we do verification off chain and how do we do verification on chain. Now, why is on chain verification important? One, that is for transparency, auditability, and also trustless validation of computations. So you want just to be transparent, or you want your proofs to be audited. So if that is the reason, then you want to do it on chain so that you can have people auditing what you've done on chain. Now, so our flow, what is the flow of our today's lesson? The flow, one, we will do Noah circuit compilation, define our ZK computation. It could be hash check, it could be range check, it could be voting, and so on. But we have to come up with a Noah circuit, that is the underlying point. Then after that, after the circuit, we'll do proof generation using BB proof to generate a proof and public inputs. Then after that, we will get the solidity verifier, generate the solidity verifier, the verifier.sol. We've been doing this in our previous lessons. So if you are not familiar of how to come up with, first of all, a circuit in Noah, proving generation of the verifier.sol. If you're not familiar with those, then it would be good you check in our previous lessons so that you are familiar with what we are doing in today's lesson. So once we obtain the verifier.sol, the next thing we do, and we did this in our last lesson, is to deploy it to Sepolia. And I showed you how to deploy the solidity verifier to Sepolia. And of course, we are using testnet to do this. We have free ETH, Sepolia ETH, that assist us to do this. We are not using our real coins, our real ETH, using ETH that is free for testing. Then we will write Foundry scripts that does the automation for interaction. Of course, we've been writing Foundry scripts previously and we've been automating, for instance, automating proof generation. We did that. We automated even generation of the solidity verifier using build.sh. So we are very much familiar with writing scripts. Even this Foundry script, we wrote it in our last lesson again. So this is the workflow, how it works. First, we do a write in our circuit. Second, we do proof generation. Then we get the verifier contract and deploy it to Sepolia. And then we follow with the Foundry script to do interaction so that we just interact with it on chain. And of course, we've already said why we require this verified sol on chain and why we want to interact with it on chain. We've already said we want it on chain because of one, transparency, and two, for auditability, and three, for trustless validation of computations. Those are very important reasons as to why you have to go on chain. Now, the summary of our workflow. The summary of our workflow is here. I've said the first thing we'll be doing is circuit, compiling the circuit. Of course, we know how to create a project. We know we'll be using, for instance, you may want to use WSL, and inside WSL, let me just again, for the sake of those who are joining us for the first time, you would want to go to where you store your programs. For instance, me, I usually store under Rust programs. So you cd Rust programs. Then after that, you would make a directory, and then the name of the project. Let me say you want to have lesson 1 as your project, lesson 1. So that's the name of the project. So make a directory lesson 1. Then when you press enter, you can now cd lesson 1. Can you cd lesson 1? Get inside this lesson 1. And while there, you can now make another directory and call it circuits. This is where we want to put our nago.toml. Our SRC will be here. So when you press enter, you then cd circuits, get inside circuits. And once you're inside here, you can say nago inish. Now, when you press enter, it tells you that the project has been successfully created. And of course, you can do these steps practically. You can do them practically. And you see it says the project has been successfully created. Now, once the project has been successfully created, you get out of circuits so that you are in your main directory, which was lesson 1, and do code space dot code, then space dot. This opens for you the VS Code, where you can now edit your main.nr, write the circuit you want there, and then you do nago compile. So that is the step we are in now, nago compile. And after that, you can also write a script for, or if you don't want, you can do proof generation. And we have a command we shared in our previous lesson on how to do BB proof. Before this, you have to generate verification key, VK. And again, we gave a command for doing that. In our previous lesson, is a command for generation of the verification key. Now, so step by step, Nago compile. You can also have Nago execute to give you witness .gz, give you a witness. Then after this, generate verification key using a command we shared in our previous lesson on generation of verification key. Now, this will be stored inside the target. Will be stored inside. You see, our circuit has target. Now, inside this target, you would now have the verification key. Of course, you already have, supposing the name is lesson one, we already have .json of this, .json. And when you did Nago execute, you got .gz, which I said is the witness. And now when you've done, you've used the command we shared for generation of the verification key, you now have the verification key also inside the target circuit. Then inside the circuit, you have target, so a verification key. Now with this verification key, and with the command I'd given you for generation of the proof, in our previous lesson, you generate a proof. You generate a proof. And this proof will also be inside target. And of course, when the proof is generated, the other thing that will be generated will be public inputs. You recall that we have public inputs and the private inputs in this ZK proofs, where the private inputs are those that are only known to the prover, and the verifier does not get to know what they are. And the public inputs are known to both parties. So these are the ones that will be found inside target. They will be found inside a target alongside the proof and the verification key. Now, after you've generated the proof, and we have a command for that in our previous lesson, we also have a command for generating a solidity verifier, which we call verifier.sol. Verifier.sol. So use that command to generate verifier.sol, and it will also be stored inside the target. So our target has various things, but this one, we will create another folder, call it contract, and we move it there. We will move it to contract. Now, this contract is not new to us. We've been having it quite some time. Every time we've been doing these circuits, we've been having contract. So everything we had inside contract remains there. And this was part of the things we had inside contract, but you see its original place is target. So we just move it to contract. While in contract, it meets several other things. The same things we had in contract, like starter dot sol. We had several things inside contract. Of course, in today's lesson, I'll be telling you what else we can generate inside contract, but I'm already referring to what we've just been having inside the contract in our previous lessons. Now, this verified sol, we move it to contract and is what we'll be deploying to Sepolia. We'll be deploying this to Sepolia. Once it's deployed to Sepolia, we'll now come and interact with it. And interacting with it will be assisting us to verify the proof. Will be assisting us to verify the proof. So we're just interacting with it for the sake of it. We're interacting with it just to, one of the reasons is to be able to verify the proof that we have. And that is the goal of our today's lesson. That will be the end goal of our today's lesson. So we will write, after we've deployed it, we will write Foundry script. And this Foundry script, one, to assist us interact with the solidity verifier, and also assist us to verify the proof on chain. Assist us to verify the proof on chain. Now, the result of these two will be, we'll have logs and results. So when you do that, you get some logs and some results. So that will be our end game for today's lesson. So that was overview of what we want to do. And then we just look at the introduction of what we'll be doing. So what we'll be doing first, as I stated in our previous slides, is we will want to deploy Solidity Verifier contract for Noir ZK proofs on Sepolia testnet. And we did this in our previous lessons. We gave you some precautions for doing this, how you be using your private key, ensuring that this private key is not exposed to public, how we did that, and so on. Now, apart from this, our today's lesson, the other thing is using Foundry scripts. And we are saying that Foundry is important to us because it acts as our automation tool that runs scripts, broadcasts transactions, and reads events. So that's what Foundry will be doing for us. It will act as our automation tool that runs scripts, that broadcasts transactions, and then reads events. So it's a very important thing. We install it. I showed you how to install Foundry in a previous lesson. You can always go back to our videos and see how we install Foundry. Or you can get the information online how to install Foundry because you're required. What are our goals in our today's lesson? One, interact with the deployed ZK verifier contract. So we had already deployed it, so we'll just be interacting with it. I'll be showing you how to interact with it. because we already deployed it, it was a hands-on class. We did our hands-on class. I showed you all the steps and how to deploy. Then I showed you how to go to your deployed contract and see it. Then at the end of the lesson, I said we will then begin from there to interact with it. I'll also show you how to distinguish between read-only versus state changing. So that is the difference between local and on-chain calls. I'll be teaching you also how to store verification results for transparency and audit. And we said this is for this reason we are deploying things on chain just for transparency and audit. Now, the Foundry script for interacting, that is again, I'll take you through how to create it. The Foundry script for interacting with your on-chain contracts. This is just again a reminder of what we did in our last lesson. How do we write it? That is the point here. So first of all, before we see how to write it, the script uses Forge, a standard library for scripting and console output. It reads the proof file from Noir build folder and calls the verifiers verify function. So that's what it will be doing. And I'll be showing you the script in a few minutes time. So it reads the proof file from Noir build folder and calls for verifiers verify function. Why is it important? Now it ensures that the proof and the inputs match those that are used during proof generation, because when you did proof generation, you had some inputs, and then there's a proof that was that resulted when you generated it. So the Foundry script here wants to verify that the proof and the inputs that are on chain match those that were used during proof generation, so that you don't have something that is on chain and is different from whatever was used. They must match. So the Foundry script we'll be using is the interact.s.sol. And again, this will be domiciled inside contract. Inside contract, we have script. And then inside script, we put this, we create this file, interact.s.sol. Now, the next important thing is to show you what we copy paste into this file, and we will be using it. So once you create that interact.s.sol, and remember you created inside script, you know where script is inside contract because we've been looking at this for quite some time now. We have contract, then inside contract we have tests, we have script, and so on. Now, so the interact.s.sol, the code that is supposed to be there is this. We have some imports. We're importing scripts from Forge standard script.sol. We're also importing console from Forge standard console.sol. and then we import, and this is coming from our contract, the verify.sol. So we import it from verify.sol. Now, this script, this is where our contract was deployed to. This is where our contract was deployed to, because this lesson assumes you already deploy your contract. And I showed you how to deploy. And of course, we deployed it in our last lesson. So beginning from our last lesson where we deployed, you copy the address where you deployed, and that address is beginning from here. This is the address where we deployed it to. That is the only thing I think I should mention there. And the other thing I should mention here is that you must also now declare the public inputs. The public inputs. These are the same inputs we used for proof generation. And so you declare them here. Remember, we just want to verify that whatever was used in proof generation is still the same thing. So these are public inputs that declared here. So I've used two. Mine, the circuit that I had two public inputs. Yours could have one public input, so you only have one here, or could have three, could have four, could have even a million public inputs. So you can list all of them here. List all the public inputs. So we just want to verify the proof and verify the public inputs. Just be verifying those. Now, this is the entire script for interacting with our Solidity verifier on chain. It's the entire, so you can just take this and customize it for your use. You customize it for your use. If you did generate your proof via Solidity, via Noir, if your ZK proof is generated via Noir, then the rest of these remain the same. You only want to change this because this now depends on where your verifier or contract was deployed to. This address is what will change for you, but the rest remain the same. And the other thing that will change for you would then be the public outputs here, inputs. The ones you used, how many they were. If there were two, they were one, and three, and so on. So the rest of the code remains the same. That's why I'm saying you can take this code and just customize it to work for you, because you know how many inputs you used. Sometimes you could even have zero public inputs. And so that means you're not declaring any public input. Those are the only places you would want to change as you customize these the script. Now, I've put here a very important tip that you can use. I've said the proof is just a serialized byte array representing a cryptographic argument. So Foundry converts this into call data that the verifier can interpret into the Ethereum virtual machine. So it's just a serialized byte array, and it represents a cryptographic argument. So what Foundry does, Foundry converts it into call data. And this call data is what the verifier can then interpret inside the EVM. So that is what we must know about proof. Now, we have created this interact.s.sol. The next thing is to run it so that we interact with our contract on chain. So before you interact with it, you run this in your terminal, and you must be inside contract. So you cd contract, because that is where your command, the interact.s.sol lies. So you run this source, there's some space here, .env. Remember this env we talked about last time, and we said that we would ensure that it's inside gitignore.gitignore, because this is what has your URL. It has your URL, and but what is important is the secret key. The secret key, the one we got from our MetaMask, the one for your account, the one for your account, and we said we must ensure that that key, that private key, is not revealed to the public. So it's inside this .env, and this .env is, you ensure that it goes to your gitignore if you wanted to have your code on your GitHub, so that when you commit it to GitHub, your .env should not be seen on your GitHub. Your repo should not be seen on your repo. It should remain in your local machine. Now, so that is just about reminding you about this .env. Now, after running this, you would then run this. You only need to replace this with your Sepolia RPC URL, and this RPC URL, of course, you get it inside your env. That is where we store it. And the private key, you can also get it inside your .env. That is again where we put it. So all these, you get them inside here. We stored them here when we began this lesson. When we extracted our private key, we stored it here. When we extracted our Sepolia RPC URL, we also stored it here. So just go back to your .env and get them, and then replace. So when you get your RPC URL, replace this entire thing with the exact code, the exact URL. And then when you get your private key, replace the entire this. Of course, you can also write this command so that it's one continuous line. It can be one continuous line, but if you want it to be the way it is here, then you're only replacing, beginning from this $sign, the entire thing, you replace it. Beginning from this $sign here again, the entire thing, you replace it. There's some space here, there's some space between that, and that space should be maintained. And then you run this command in your terminal. Now, when you run this command in your terminal, just do it. And when you do it, you should get this as part of the expected output. Among several other things, what is important to us is verification result, true. If it says true, then it means your proof is valid. If it says false, then it means your proof is not valid, is invalid. But you should get one of these. You should get one of these. So the first one just means that the proof that you trying to verify agrees with the one that was generated when you are generating. So if it agrees, then it means it's valid. If they do not coincide, then it means it will be false, therefore. That means it's invalid. Now, just before we go far, we need to understand the difference between read and write, or read versus write. Because the last time we deployed our contract and verified our contract, we discovered that there was something read and there was something write. And those are the things we need to know, what they mean. What is this read and what is this write? Now, so there's something I've said about local and on-chain interaction. And I've said read or view. But for us, what we saw was read. Executes locally, and there's no gas fee for this read. You're not charged for it. And it doesn't modify blockchain state. What that means is that when you read locally, your contract on chain will not be seen as having been verified, will not be ticked. We saw how it ticks when it's verified, and then it gives us our compiler and so on. But if you're doing it locally, those things will not appear. That's what I mean. It doesn't modify blockchain state. What about write? Now, this one, it's broadcasted to network, and therefore, because of that, there'll be gas costs. Then it will also update contract storage. And so when you go on chain, you would see that the contract has been verified successfully. And therefore, even the color changes, and you would see the compiler that was used, and so on. Now, there's some insight here for you again. And I'm saying that calling verify function through Foundry would stimulate a local EVM, Ethereum virtual machine call, same as using the read contract feature on the Etherscan. So they're doing the same thing, only that one is doing it locally and the other one will be doing it on chain. Now, so you've done it locally and you've done it on chain. Why do we require it on chain? Why do we think that doing it on chain would be more important? Of course, we already stated a few advantages. And one of the advantage we said is that when you do verification on chain, one, you would enable public auditing of which proofs were successfully verified and which ones were not. So somebody can see that the proof was successfully verified or the proof was not successfully verified, and therefore it does not it does not conform or is not the same as the one that was generated locally, in other words. The other advantage of verification on-chain is that it simplifies integration into front-end dApps that react to verification events. And also, lastly, it creates a verifiable record that is very useful for ZK attestations and a decentralized identity. So these are very important points that then mean that we must know how to do on-chain verification of our proofs. So we must learn to do the on-chain verification. And just an example to emphasize the importance of this on-chain verification, the real-world example is the privacy-preserving voting system. So supposing you did verification on-chain, that means your proof is stored on-chain. So the results are on-chain, and therefore anybody who wanted to audit the outcome of the results, like the observers, if, for instance, supposing they wanted to see the outcome, they would come to confirm which votes were valid and which ones were not. So they'll be seeing this on-chain because you did a proof verification. So when you do proof verification, your data is stored on-chain. Anybody wanting to audit, anybody wanting to verify would come and just see what the results were. So this is an example, the privacy-preserving voting system. So storing proof results allows election observers to confirm valid votes. And because you're doing it ZK, it means they can confirm the election votes, but at the end of the day, they will not get to know voter data. They will not get to know voter data. So they'll not know who voted. That is what I mean by voter data. They will not get to know the voters. Now, so because we've seen that it's important to do our verification on-chain, I now want to take you through the process of doing verification on-chain. What Foundry script are we going to write? And how do we write this Foundry script that would then assist us to do verification on-chain? Now, so to achieve the on-chain verification, we would create Hong verification record, no, Hong verifier with the record.sol. And we are doing this inside contract folder, the same level as the verified.sol. So you see, you have the contract, you have contract folder. Now we said this, we have under this, we have files that are just fall inside here. One of them is the verifier.sol, verifier.sol. The other one is this Cyprian verifier app.sol. And then the other one will be this Hong, the one we are creating, Hong verifier with the record.sol. Of course, the other one will be test, but inside the test would have things like starter.t.sol, and you know what is always here. And the other thing that will be inside contract will be script. And inside the script, we've seen we've already seen, okay, there are the other things inside here, but the other one that we've just seen is the interact.s.sol, the one we just created above, the one we just created above here, this one. Interact.s.sol. It's inside script. So these are the things that are inside our contract. So when I say that the home verifier with the record.sol should be the same level as verifier.sol, this is what I mean. That they are not inside another folder. They're just inside a contract. But inside the contract, they're not inside another folder, or they're just inside the contract. Like look at this. This is inside the contract, but it's inside another folder called tests. This is also inside the contract, but it's inside another folder called script. But this, the home verifier with the record.sol is at the same level with the verifier.sol. Remember the verifier.sol we said originally was inside the target and we moved it to contract. There's some security tip here. And I've said that always validate that only authorized functions write state or emit verification events. Only authorized functions should be allowed to write or emit verification events. Misconfigured access control can lead to false verification records. And so we should be aware of that and prevent it. As a security tip. Now let me just share with you the code that you would have to paste inside the home verifier with the record.sol. Of course, it will be almost the same code for you, just a few changes. You can customize it, and I'll be showing you which areas you will maintain and which areas you would want to customize. So this is the code. Begins the only one import here, and we are importing the verifier.sol. This is what we will be deploying on chain. We don't deploy the verifier.sol. We deploy the honk verifier with the record. And once you deploy this, since you've imported the verifier.sol, the verifier.sol will appear under it. So it would be like you also deployed the verifier.sol, but you're not deploying verifier.sol, you're deploying the honk verifier with the record. But when it goes on chain, it goes together with the verifier.sol. So that is again just a clarification. We will not from now hence be deploying the verifier.sol as we did in our other lessons, but we'll be deploying the honk verified with the record, and we expect that once it reaches on chain, the verifier.sol will also be there because it has been imported. Now, so the rest of the code remains the same. The only place you would want to change would be maybe the public inputs, declaration of the public inputs, and the rest remain the same. So in fact, you can just maintain the entire code. You can just maintain the entire code and it will work for you. Yes, because everything it has is what you require. Once you have this code, how do we deploy it? Because we've said what we'll be deploying will be the honk verifier with the record, and you can see I've said forge create. There's a dot here, honk verifier with the record dot solve. But before that, you did forge build. You did forge build, and after forge build, you come and deploy, and this is the code you're going to use. So you only change this part and change this part. Now you remember this is the same command we used when we were interacting on chain, but the difference comes in at this point, and this remains the same thing. This remains the same thing. So the difference is only this part here, but the rest remain the same thing. So that you're not confusing these codes, you're not saying that let me just take you to the previous one. The previous command is here. You can see forge script interact.sol.s.sol, and then here interact honk verifier interact honk. So this is the only part that is different in the two commands. So it's just almost the same command, you just change the upper part, and once you change the upper part, it does a different function. It will do a different function depending on the upper part. So if the upper part is this, then it knows that it's supposed to interact with the contract on chain. And when you come here and change the upper part, then it must understand that this is meant to deploy the honk verifier with the record.sol. I'd already told you that this you'll be going to .env and copy it and then replace the entire thing here. The same to this. The private key is already inside the .env. Go get it and then replace the entire thing. And then you run this in your terminal and it deploys this contract. We will follow this contract to go and interact with it on chain. Now, when you go on chain, you should be able to see compiler version. You'll be able to see upload. You'll be able to upload all relevant .sol files. They'll be there uploaded because you had imported them previously. You had imported verify.sol here. And so because of deploying this, you would have all of them deployed, uploaded. They'll all be on chain. Now, to interact with them, we'll go get the proof, of course, and the public input, and then I paste them somewhere, and I'll be showing you how to do that so that you just confirm that those are the exact ones and they match with the ones that are on chain. This is what I said. It will be a confirmation that the contract has been verified. The green check mark, that tick green check mark, when you see it on the contract, it means the contract has been verified. Or if you don't see it, it means it has not been verified. Now, the interact.s.sol that we had assisted us to interact with the contract off chain. It was to assist us interact with the contract off chain. But if you want to interact with the contract on chain, what you require is not that interact.s.sim. What you require is store interaction.s.sol. Store interaction. So this one will also be inside the script. So inside the script, if you're doing it on chain, then the script would have this, not the interact.s.sol. The interact.s.sol was inside the script because at that point we wanted to interact with our contract locally. But if you want to interact with it on chain, then this is what you want to have. And this file, we just paste this, is almost the same as the interact.s.sol, apart from just a few areas. So when you compare them, you will find that they are almost the same, but they will just vary a few areas because we want this to interact on chain. We'll be doing the on-chain verification. So those are the only areas that would then vary, but the rest will just be the same. What you will be importing here will just be this. Just be importing the script.sol, not so many things as we did in the interact.yes.sol. But then this will be where you deployed it. So you replace this with the exact address where you deployed it, where it's deployed. And then the same explanation as we had previously for the public inputs. And so this code would work for you if you would just change this part and replace it with your exact address where it is, where you deployed it. And then again, replace this with your public inputs, depending on how many they are. There could be none, 1, 2, 4, and so on. So if you were to change those two positions, then this code would still work for you. Now you want to on-chain, you want to do on-chain write execution. So I've said before you do that, first of all, this one speaks about this, and I've already said what you're supposed to do with it, that you're supposed to replace it with the address you obtained when deploying your home verifier with the record. Now, we will then run this. Once you have this code and you want to go on chain and interact with the contract, you would then run this. This is the code to run. First of all, you would run this as we did in our previous example. You would run source.env, and remember there's some space here. Then the second thing you would run this code here. So this is the code you would run, just change a few things, ensure that the RPC URL is yours, ensure that the private key is yours. Those are the only two things you need to change, and you run this code. Remember, this is the same code we've been using, and I'd already said we're only changing the upper part. We're only changing the upper part, and it performs a different function for us, but the rest remain the same. And by the rest, I mean the RPC URL remains the same, the private key will remain the same, then we would want to broadcast. So those ones remain the same. When you do this, what are your expectations as the output? Now, we expect Forge to compile and then submit a transaction to Sepolia, and that transaction would call verify and store. And then we also expect transaction logs to appear. Once mined, the verify and store writes the last verification and the last public inputs on chain. So when you go on chain, you're able to see what were the last verification and what were the last public inputs. So those ones will be written. Those are the logs we are referring to, the transaction logs. So it's telling us what were the last verification and what were the public inputs. These ones will be there for anybody that want to edit, to audit. Anybody wanting to audit will come and see those logs. And then I would also expect event proof verified is emitted if the proof is valid. And of course, if the proof is not valid, again, we would know, we get it to know. And then the other thing we expect is the console.log output that shows that verify and store returned true. It could also return false, of course, but that is what it's supposed to show. So we expect it again. Now, what are the results on Sepolia? I've already said what we expect to see there. So when you go to Sepolia, you are supposed to see transaction mined, and then last verification, true, event emitted, a state visible on Etherscan. So in Etherscan, you'll be seeing last verification, last public inputs, and then event logs. Now, okay, of course, if you wanted to see all this, you would retain the same link up to this point, and then change this, replace it with your address. So when you replace this with your address and then go to your browser, you're able to see your contract where it was deployed, and you're able to see all these logs. You're able to see these logs. So you just maintain the same link, only change the address, and you're able to go to your browser, and you're able to see the logs. Now, what are the common issues and how do you troubleshoot? Now the common issues: one, incorrect proof file path. For instance, you may see file not found error, or you might find an error that says mismatched public inputs, or verification always returns false, or you may see wrong RPC URL or missing key or transaction not broadcasted. So those are part of common issues you may meet in this project. But if you used the correct steps that I illustrated, then this may not be issues for you. What are the useful tools that we've used? We've used Forge, Inspect, Check, Contract ABI, we've used Cast Call, Quick Manual, Contract Call, Sepolia, Etherscan, Logs, Confirm Emitted, and so on. Those are the tools that you require. So a few takeaways and summary in our today's lesson. We've looked at how to, from the start, how to create Noir circuit. And we said that Noir assists us to produce ZK proofs, but Foundry would bring them to blockchain. So Foundry will assist us to bring these ZK proofs to blockchain. So Noir would just assist us to produce the ZK proofs and stop at that, but Foundry takes it from there and then takes these ZK proofs to blockchain. Now, if you wanted to read only verification, you can do this locally. And this local verification works just like the one we are doing on-chain. It does just like what the on-chain one would do to stimulate the EVM. So the local one will also do something like that, so that we are able to verify the proofs. Now, but the on-chain one does something different, that it stores your proof locally, no, on-chain, and this has the advantage of transparency, accountability, and also for composability. That's the advantage of having it on-chain. The other thing we need to recall from our lesson is Sepolia testnet is ideal for experimentation. Before you do the mainnet deployment, you must do the testnet, just to be sure that things are working as they're supposed to. And then keep your private keys safe always, and use test accounts for practice, so that you're not using your accounts that have real ETH for practice. The next step will be to integrate verifier with front-end UI using ethers.js or VM to visualize real-time proof verification. So that is what we were to cover today. And if you wanted to read more, the references are here. You can find Noah ZK language here, just clicking on the link, or copy the link and paste it in your browser. If you wanted to install Foundry or learn more about Foundry docs, then again, we have that. Ethereum Sepolia testnet, wanted to know more about it, that is the link. If you wanted to know about ZK Snacks overview, and again, that is the link there. For questions, these are the contacts. if you had questions or wanted to reach out. Thank you.